Today I want to talk about Class 2 rapids. Just kidding. Today I want to talk about Class 2 projectile motion. Class 2 projectile motion is an arbitrary, well, not arbitrary, but it's a unique distinction that I like to make between the projectile motion problems. Class 1 projectile motion problems go off a cliff horizontally, like that, and then follow a parabolic trajectory like that. But a Class 2 projectile motion problem is something like this. Maybe there's level ground and you've got something that's being kicked. Or here's a guy about to kick this ball. Yeah, here it goes. Phew, and it goes like that. That's a nice Class 2 projectile motion. This ought to be a symmetric parabola. It's a little bit sloppy here. Maybe I'd have it go like that or something. But a Class 2 projectile motion problem is significantly harder because the initial velocity, here's what I'm going to write, the initial velocity in the y direction is not equal to 0. So I found this really wonderful Class 2 projectile motion problem that has h different parts, and we will just work our way through it. It's from the New Jersey Center for Teaching and Learning, so that's NJCTL.org, and I'm teaching one of my classes off of their curriculum. I think it's pretty solid stuff. So, you know, there are a few mistakes, but it can be improved, and that's always good, but the idea is right. So here's the problem. We got this high school football game, and there's this field goal being attempted from just outside the 30-yard line. I don't want to talk about yards, I want to talk about meters. So thank goodness we have converted into meters for the rest of the problem. The total distance from the ball to the goal post is 40 meters, but that's not delta x for the ball. The ball might go further, or it might not even go that far. They haven't told us that yet, so be careful. It says the crossbar of the goal post is 7.3 meters high. And to be good, a field goal attempt must pass over the crossbar, right? Any distance above the crossbar will be fine. The velocity of the ball after being kicked is 25 meters per second at an angle of 37 degrees above the horizontal. I like 37 degrees because I'm thinking it's a 3, 4, 5 triangle. So before I even read any of the questions, I know that I need to draw my initial velocity vector. And here's what I'm going to do. I'm going to take the problems away and then bring them back only when I need to write them down. So if you want to write down these problems right now, you could, or just print the screen or something, whatever. Yeah, move this over to the side so we can get some work done. I'm going to take this initial velocity vector, and the initial velocity vector is 37 degrees above the horizontal, and I need to resolve it because the velocity in the x direction and the velocity in the y direction behave very differently. In fact, one of them will be changing and the other one will not. So here's my initial velocity, and we could call it VI or we could call it V naught, and let's go British on this sucker. V naught is 25 meters per second. What about V naught in the y direction and V naught in the x direction? Those are the things that I would probably also want to know. Well, it looks like this is going to be V naught y is probably going to be V naught, that hypotenuse, right, times it, let's see, it's opposite, so it's going to be the sine of theta, and this guy is V naught times the cosine of theta. And if I follow my 3, 4, 5 triangle, look, this is 5 times 5, so this guy will be 3 times 5. It's probably going to be 15 meters per second in the upward direction. And this guy is going to be 4 times 5, so it's 20 meters per second. There's a little bit of error on these, but I'm assuming it's not exactly 37. It's like the angle that gives us a 3, 4, 5 triangle, 36.9 or so. I don't know. I don't want to talk about it. Here's what I want to do. I want to address the questions and see what they want to know about this problem. But I wanted first to resolve the initial velocity vector. That you must do before every problem, because there's acceleration in y and there's no acceleration in x. All right, here's the plan. Determine the horizontal component of the ball's velocity just after being kicked. Oh, cool, we've done that. That's 20 meters per second. So I'll write down A 20 meters per second. That's the horizontal component. What about B? I should write it out for you. That's the initial in the x direction. And B says, determine the vertical component of the ball's velocity just after being kicked. Well, shoot, I guess we did that too. 15 meters per second. The nice thing about the New Jersey Center for Teaching and Learning is that they are walking us through this problem with each successive step. So in our initial step, we've already done their first 2 requests. What about part C? Determine the horizontal component of the ball's velocity at its highest point. Oh! Well, now we're talking about a parabola. And we're talking about up at the top right here. I want to know how fast the ball is going in the x direction at this moment. Now the nice thing about it is the initial velocity in the x direction is the final velocity in the x direction because there's no acceleration in the x direction. So I just write down, hey, you want to know the final velocity in the x direction? It's the initial velocity in the x direction, which is 20 meters per second. Let's do part D, see what it has in store for us. Part D says determine the vertical component of the ball's velocity at its highest point. Everybody knows that to get to the top of a hill, you have to stop going up. And you have to start going down. But in between stopping going up and starting going down, you have to be stopped. You have to actually stop. So you will not be going up and not be going down if you're at the top of your path. So the final velocity in the y direction, and I'll say Vy top, so we can be really clear about that, is 0 meters per second. No problem. What about E? Determine the highest point of the ball's path. Oh, now I need my kinematic equations. I'm gonna walk over here and get them. Oh, found them. I want to know how high the ball is at the very, very highest moment. Which equation will give me delta y for the ball? Well, I guess this one would, and this one would, and this one would. My preference, though, is to use the fact that we just figured out the velocity in the y direction is 0. So that's almost always going to be the way that we attack these problems. That is the weak point on the problem. At the top, the velocity in the y direction is 0. So I'm going to take this guy, tail of 2 squares, because I know that the final velocity in the y direction at the top is 0. And that will give me delta y at the top. So we'll have to do a little bit of math to do this sucker right. I'm going to write down, first, using that equation, I write down 0 equals, here, I should preface it by saying at the top. 0 equals the initial velocity in the y direction squared plus 2 times the acceleration in the y direction times delta y. And I'm going to solve that sucker for delta y. That's a pretty quick operation. Negative v naught in the y direction squared divided by 2 times ay is delta y at the top. And now New Jersey requests that I solve that problem, so I go over here and I get my velocity in the y direction, which is 15 meters per second. I put a minus sign in here, I go negative 15 meters per second squared. I'm not squaring negative 15, but I put a minus sign in front of the whole thing, and then I divide by, now careful, I want to divide by 2 and I want to divide by ay. So I'm going to open up some parentheses, divide by 2, multiplied by, negative 9.81 meters per second squared. Now the nice thing about it is I don't need those 2 minus signs, so if I'm feeling slick, I can just hit enter really quick. So I got this this height of the football to be 11.468 meters. Now that's how high up the football is, but we probably want to do sig figs on that sucker. I think we only have 2 sig figs to work with right here. So that's going to be 11 meters, and I'll call that delta y at the top. I can't say that it's just delta y, because delta y could be anything, but we used this work that was at the top, and I'm getting bored with this particular color, so we're going to have to go away from green for a moment. Let's tear off our work for A through E. Hopefully you've got that all written down, and I'll let you consider F while I'm getting the paper ready. F says determine the time that it takes the ball to reach the goalposts. Ooh, okay. The time that it takes the ball to reach the goalposts. All right, here is where you can find the problem. Here is what the ball is doing. The goalposts might be here and they might be here. I don't really know whether the ball is going to make it yet. But in order to determine the time it takes for the ball to reach the goalpost, I need to consider that the goalpost is 40 meters away in the x direction. So I write down delta x equals 40 meters. Oh, and I'm trying to find time. Do I know how fast it's going in the x direction? I think I do. I think that's 20 meters per second. You can check our initial triangle. Yeah, it's going 20 meters per second in the x direction. And I've got this really simple equation in the x direction. Every equation is really simple in the x direction. There is only one equation in the x direction, and I'm supposed to just divide those suckers. I guess if I'm trying to find time, I'm going to say that this is delta x divided by the velocity in the x direction. So that time then is, wait a second, are we just doing 40 meters divided by 20 meters per second? Yep, cool, 2 seconds. I'm gonna probably write 2.0 seconds because I like to have 2 sig figs. They're not giving us 2 sig figs, that's strictly speaking only 1, but whatever, we'll pretend they're giving us 2. That is the answer to, oh shoot, that is the answer to part F. We are almost finished on this problem. Part F says delta t goal equals 2.0 seconds. Now, the reason they're saying the time it takes the ball to reach the goalposts is we don't know where it's going to be vertically, whether it's just falling plop right there and that's the total time, or whether it's over it or hitting the goalpost. I don't know what's going on. But G, we're ready for G right now? G says determine the height of the ball when it reaches the goalposts. And I guess we're trying to figure out whether the field goal attempt was good or not. So we want delta y goal. And in order to do that, we need an equation for delta y. Where's a good equation for delta y? This one. And we need to plug in the time when it gets there, and that's going to be there for us. We're going to say delta y at the goal is the initial in the y direction times time plus 1/2 the acceleration in the y direction times time square. And I plug in t goal. See, I'm going to plug in t goal right here. Oh yeah, see I am, I'm about to. All right, then I go to my calculator. No, I'll write it out. I'll write out what I'm going to plug in. This is kind of silly, maybe a waste of time for you, hopefully not. Skip a bit if you want to not waste your time with this. I've got V0 in the y direction, which is 15 meters per second, and I'm multiplying that by 2 seconds. You can do a lot of this in your head, especially if you pretend that the acceleration of gravity is negative 10. So then I'm plugging in negative 9.81 meters per second squared, and then I'm supposed to multiply that by 2 seconds and square it. So I'll do all that business. Let's see, we've got 15 times 2 plus 0.5 times negative 9.81 times 4, which is 2 squared. I did that in my head for you. I got 10.38, which is a little bit annoying because when I do sig figs, I'm going to have to write 1.0 times 10 to the first meters in order to show that I have 2 sig figs on that number. All right, the final question is, wait, is the goal attempt good? Is it good? Let's see. The goalpost is at 7.3 meters, and we made it over at 10 meters. Goal! Yay! Let's put some Spanish flavor on that sucker. Okay, now, you want to go H, I want to go H also. Determine the velocity of the ball as it passes the plane of the goalposts. So I have to include magnitude and direction. That's really nice of them to note that for us. The velocity of the ball at that moment can be found with 2 equations. First of all, the velocity of the ball in the x direction is the initial velocity of the ball in the x direction. So it's still 20 meters per second. And what about the velocity of the ball in the y direction? Well, the final velocity of the ball in the y direction is the initial velocity of the ball in the y direction. Oh, I don't usually use that notation. I'm sorry, I'm going to write final velocity in the y direction is the initial velocity in the y direction plus acceleration in the y direction times time. So what time will I plug in right here? Oh yeah, 2 seconds. Because that's the time that the ball takes to get to the goal post. Whew. And we want to figure out how fast it's going when it gets right above that goalpost. The ball is actually doing this, I guess. And it's going to be like here, maybe? Something like that. Anyway, we'll figure it out, but we're going to plug in that time right there and figure out how fast it's going in the y direction. If I do all of this math, I'm saying the initial velocity in the y direction is 15 meters per second positive minus 9.81 meters per second square multiplied by the time, which is 2.0 seconds. Here we go. Here we go. Here we go. It's going to be something like -5, right? I got 15 minus 9.81 times 2. It is negative 4.62 meters. I'm going to write meters per second. Yikes. Velocity, meters per second. Units work out to be meters per second right here also. Of course so. Of course. So that's how fast it's going in the y direction, and this is how fast it's going in the x direction, but we need to draw those two and find the ultimate velocity and direction of the ultimate velocity. So I'm going to do that right here so that we don't make too much of a mess. How about we do it right over here? The velocity in the x direction as it crosses the goalpost is 20 meters per second. The velocity in the y direction is negative 4.6, so that's an arrow that goes down. It's an arrow that goes down, and it's 4.6 meters per second. The reason I didn't put a negative here is because the information that it's pointing downward is contained right there. Now I draw the resulting velocity, so the ball is going like that, because I know that the velocity final in the x direction plus the velocity final in the y direction must be these two vectors, right? If I add these two as vectors, then I'm going to get the final velocity vector. So here's what I say. The final velocity vector is, and I do p-thag to find the length of that sucker right there. Here, watch me. I'll do p-thag in front of you. I'm going to take the square root of 20 square plus 4.6 sucker square. That's 20.5. Oh, that's going to go to 21 meters per second when I do sig figs at. And I need to find an angle. This angle's right. Do I want that lower angle or that top angle? This one, because it's at the base of my resultant vector. You can go up and look at the adding vectors thing if you want to talk about that some more. But now I take the inverse tangent. Here I am, inverse tangent. Opposite, 4.62. Adjacent, 20. Whoa, careful there. And I get 13 degrees. 13 degrees though, like what is this? This is up and this is over. So I guess that's 13 degrees down from over. Or I could say down from horizontal. We have finished the problem. I'm out. To x for the ball. The ball might go further or it might not even go that far. They haven't told us that yet, so be careful. It says the crossbar of the goalpost is 7.3 meters high. And to be good, a field goal attempt must pass over the crossbar, right? Any distance above the crossbar will be fine. The velocity of the ball after being kicked is 25 meters per second at an angle of 37 degrees above the horizontal. I like 37 degrees because I'm thinking it's a 3, 4, 5 triangle. So before I even read any of the questions, I know that I need to draw a kicked, or here's a guy about to kick this ball. Yeah, here it goes. Pew, and it goes like that. That's a nice class 2 projectile motion. This ought to be a symmetric parabola. It's a little bit sloppy here. Maybe I'd have it go like that or something. But a class 2 projectile motion problem is significantly harder because the initial velocity, here's what I'm going to write, the initial velocity in the y direction is not equal to 0. So I found this really wonderful class 2 projectile motion problem that has h different parts, and we will just work our way through it. It's from the New Jersey Center for Teaching and Learning, so that's NJCTL.org, and I'm teaching one of my classes off of their curriculum. I think it's pretty solid stuff. So, you know, there are a few mistakes, but it can be improved, and that's always good, but the idea is right. So here's the problem. We got this high school football game, and there's this field goal being attempted from just outside the 30-yard line. I don't want to talk about yards. I want to talk about meters. So thank goodness we have converted into meters for the rest of the problem. The total distance from the ball to the goal post is 40 meters, but that's not dealt. Today I want to talk about class 2 rapids. Just kidding. Today I want to talk about class 2 projectile motion. Class 2 projectile motion is an arbitrary, well, not arbitrary, but it's a unique distinction that I like to make between the projectile motion problems. Class 1 projectile motion problems go off a cliff horizontally, like that, and then follow a parabolic trajectory like that. But a class 2 projectile motion problem is something like this. Maybe there's level ground and you've got something that's being kicked by initial velocity vector. And here's what I'm going to do. I'm going to take the problems away and then bring them back only when I need to write them down. So if you want to write down these problems right now, you could, or just print the screen or something, whatever. Yeah, move this over to the side so we can get some work done. I'm going to take this initial velocity vector, and the initial velocity vector is 37 degrees above the horizontal, and I need to resolve it because the velocity in the x direction and the velocity in the y direction behave very differently. In fact, one of them will be changing and the other one will not.